All right, Senior Mouth, welcome back. Here we are. We are going to continue talking about combinations and permutations today. We are actually going to combine it with our last unit of probability to talk about how we can solve some sort of types of probability questions using combination and permutation. So you had this warm up. You just got a free ticket for a boat ride. You can bring 2 friends along with you. Unfortunately, you have 5 different friends because you're so popular who wants to come along with you. How many different groups of friends could you take with you? So our first question was determining, is this a combination or is this a permutation? And then figuring out what is the total, or what is actually the answer of the question. What is the total number of arrangements you could have? So how many different groups of friends could you have as you take with you? Well, it doesn't matter whether when you pick a friend, whether they're friend 1 or friend 2, because they're both getting to go on the same boat ride. So this is an example of a combination because order does not matter. It doesn't matter if you're friend 1, friend 2, friend 3. Well, I guess it matters if you're friend 3 or friend 4 because you're not going. But friend 1 or 2, they're the same thing. Everyone gets to go on the boat ride, assuming you're picked. So we know it's a combination. So we know we have 5 total options. It's a combination, and we are choosing 2 of them. So we just have to do 5 combination 2, and that will give us our answer. So going to our calculator, we can pull up our Desmos calculator, go to functions, go to stats, go to combinations, and we know this is 5 combination 2, and we get 10 options. So our answer is 10, and that's our total number of arrangements. Pretty simple, pretty easy. That's what we were doing last week. Now we're going to look at how we can use this with probability. So permutations and combinations help us determine the total possible number or the total possible number of arrangements of certain scenarios. We can use these 2 calculations to help us determine the number of desired outcomes or total outcomes in some more complex probability questions. We'll look at a few examples throughout this whole lesson. So essentially, there's some types of questions that it's hard to figure out what is the desired outcomes or what is the total number of outcomes just because of the possible arrangements, but combinations and permutations help us be able to calculate those larger possibilities much easier. So we'll look at some examples. So example 1, in a 4-digit PIN is needed or is selected. What is the probability that there are no repeated digits? So we kind of looked at this problem a little bit earlier. Well, if you have a 4-digit PIN, like on your passcode on your PIN card or on your debit card or on your phone, what is the probability that there are no repeated digits? What is the probability that given a 4-digit code, you don't repeat any digits? Well, we know probability of no repeated numbers, no repeated digits. We know probability is desired outcomes. If I can spell desired correctly, desired outcomes divided by the total possible outcomes. So we have to figure out first, what is our desired outcomes in this situation? What's the numerator of our fraction? So what are the desired possible outcomes? Well, the desired outcomes are having no repeated digits. So given 10 digits, you are picking 4 of them and you are not repeating. So it does not matter which order we pick these in. I could have 1, 2, 3, 4. I could have 3, 4, 2, 1. Those are the same because I am not repeating my outcome. So this would be an example of a combination. No, I'm sorry. This is an example of permutation because it does not. Give me one moment. Let me check my notes really quick on this one. Actually, I apologize. All right, sorry about that. I apologize. This is an example of a permutation. It's a permutation because it does not matter, or because a potential option of 1, 2, 3, 4 is different from 4, 3, 2, 1. Those are 2 different possibilities that we could have for our example. So there are different arrangements do make a difference in this case, whether you are 1, 2, 3, 4, 2, 3, 4, 1, 7, 8, 9, 3, I don't know, whatever. As long as you're having different digits, that's fine. So this is a permutation. So we have 10 possible options, and we are permuting 4 of them. So 10 permutation 4. Now, if we think about our total number of outcomes, is essentially you have 10 options 4 different times. So you have 10 options for the first number, you have 10 options for the second number, 10 options for the last number. And so this would be 10 times 10 times 10 times 10, or 10 to I'm so sorry. 10 to the fourth power. So we have 10 permutation 4 in our numerator, 10 to the fourth power in our denominator. We can calculate what both of these numbers are. So in my numerator, I had, go to functions, go to permutation. I have 10 permutation 4, and that gave me 5,040 options for my first option. So 5,040 possible permutations. For 10 to the fourth, we can just plug that in as 10 raised to the power of 4, and that gave us 10,000 options. So we have 5,040 out of 10,000 options. If we divide those two, going back to our calculator, we do 5,040 divided by 10,000, and we get 0.504. So there is roughly about a 50% chance, just shy over a 50% chance of having no repeated digits out of all of the possible digits. Now, is it common for someone to probably pick the same digits? Maybe. Maybe if they have a favorite number, they might pick that favorite number multiple times. But given all of the possible options, the probability of them not repeating a digit is roughly about 50%, just a little bit over 50%. Let's look at another example. In certain states, lottery, 48 ball, or in certain states, lottery, a 48 balls numbered 1 through 48 are placed in a machine, and 6 of them are drawn at random. If the 6 drawn numbers match the numbers that the player has chosen, the player wins $1 million. In this lottery, order does not matter. The order of the numbers are drawn doesn't matter. Compute the probability that you will win $1 million prize if you purchase a single lottery ticket. So we're looking for the probability that you win, essentially, the probability that you get those correct 6 numbers. Now, once again, they said order does not matter. So if you choose the numbers 1, 2, 3, 4, 5, 6, and the numbers show up as 6, 5, 4, 3, 2, 1, you still win because you got the same order, or because you got the same numbers. It does not matter for order. So in that case, we know it's going to be a combination because order of arrangements does not matter. So if we think about desired outcomes out of total outcomes, our desired outcome is our 6 digits are chosen. Now, it does not matter how many times or which arrangement they're chosen. We just have 6 digits that need to be chosen. So essentially, we have 6 combination 6. So from our 6 digits, they are chosen. Now, it does not matter the arrangement, which essentially 6 choose 6 is just 1. So this is going to give there's one type of combination that we are hoping to get. Out of how many potential combinations? Well, let's find out. If we think about the total combinations, we have 48 total balls that can be chosen. 6 of them are going to fall through the tube, and 6 of them are going to be picked. So 48 combination 6 is the total number of combinations that we are looking for. And we just want one specific combination, which are the 6 numbers that we have chosen. So we are going to figure out what is combination 48, 6. So 48 combination 6 gives us, let's see, that is 12,271 or 12,271,512 possible combinations. So that is 12,271. Is that 1271 or 1217? 1271, 5, 112. So 12,271,512 out of 1. So all we have to do is do 1 divided by that previous answer, which we said was 12,271,512, gives us 8.14 times 10 to the negative 8th, which is essentially 0.00000008, which is a very, 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 very small number. That is, let's see, tens, hundreds, thousands, or yeah, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. You have one 8/10 millionths of a percent, or 8/10 millionths of a decimal, essentially, or 8 out of 100,000th percent of a chance of winning. So your odds of winning are almost zero, pretty much almost 0%. Now, it's not impossible. There is a chance of winning, but it's very, 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 very unlikely that you win. But understandable, that's a chance of winning $1 million, is you have a very, very small chance of winning. Now let's get example 3. So in that state lottery from the previous example, that one we just did, if 5 of the 6 numbers are drawn, matching the number, the player wins the second prize, which is $1,000. So if you go and get 5 numbers right, you still win $1,000, so it's not a total loss. Compute the probability that you win the second prize if you purchase a single lottery ticket. So we're looking for the probability of winning $1,000, which we, once again, we know is desired out of total. Well, the desired outcome, if we think about our desired outcome, we want 5 out of 6 numbers chosen, any 5 of our 6. So if we have our 6 potential numbers that we picked, we want 5 of those chosen. The last number that is chosen, because there needs to be a 6th number, it needs to come from one of those any possible numbers that was not picked. So out of the 48 balls, we picked 6 numbers. We're hoping 5 get picked. So there are 42 other options out of the 48, and we want one of those other 42 numbers, which essentially is just 42 potential combinations. But so this first number, this first combination here, this is 6 combination 5, which is saying out of our 6 numbers, we are choosing 5. And then out of the 42 other numbers, we want one more option. So we are going to multiply those together. That is our multiplication property. When you have multiple combinations, you can multiply them together. Now, once again, the denominator is still going to be 48 choose 6. That's still going to be the total possible combinations that can show up. So the denominator is the same. It's just whether our prize winning is different. So we need to figure out, so 6 combination 5 times 42 combination 1. Now 6 combination 5 is essentially you are out of 6 total numbers, you are choosing 5 of them, which is essentially saying you are leaving away one of those options. So there are 6 potential balls that we could leave. So if we put 6 combination 5, you're going to get 6 in the calculator. I'm just saving us time. If we put 42 combination 1 into the calculator, that's saying out of 42 options, you were choosing 1. Well, you're going to have 42 options. So it's going to be 6 times 42. So 6 combination 5 equals 6. 42 combination 1 equals 42. We already figured out what 48 combination 6 was. That was 12,271,512, I think. 512. So if we put this in the calculator, we first have to figure out what is 6 times 42. Well, 6 times 42 is equals, why did you not equal? Oh, I didn't hit enter, sorry. 6 times 42 equals 512, or sorry, 252. 252 divided by our big number, which I'm just going to draw that arrow to show that it's going over. Let's see what that is. So we should have a better chance of this happening. Not going to be great, because we're still dividing by 12 million. Divided by 12,271,512 equals 0.000002. So is that 4 zeros ahead of us? Okay. Which is roughly 0.002. So this is only about 1/1000th or 2/1000ths of a percent. Not that bad. Not as bad of chances. There's more of a chance. But once again, you're only winning $1,000 compared to $1 million. So we can still calculate those combinations using those arrangements. Compute the probability of randomly drawing 5 cards from a deck and getting exactly 1 ace. Compute the probability of randomly drawing 5 cards from a deck and getting exactly 1 ace. So given your 5 cards, we want exactly 1 ace. Now, when you draw cards from a deck, typically once you get those cards in your hand, you can rearrange them, and that's fine. So unless the question specified otherwise, we can assume that you can rearrange your cards. So we can assume because you can rearrange your cards that it does not matter which order they're drawn in. Because if I get an ace, a 1, a 2, a 3, or if I get an ace, a 2, a 3, and a 4, I could rearrange those to be a 3, a 4, a 2, an ace. And that's fine. So this is a combination, once again, because order of being drawn does not matter. So my probability of getting exactly one ace. So we just want one ace. We don't want two aces. We don't want three aces. We want one ace. If I think about the total possible combinations, there are 52 cards in a deck. There are 52 cards. So I'm going to be dealt out of 52 cards. I have a combination of 5 cards. So out of those 52, I'm getting a combination of 5. So 52 combination 5 is going to be our denominator because that's going to be our potential number of combinations for hands we could get. Now, if I think about the number of cards, there are 4 aces in the deck. We have 4 types of suits. We have hearts, spades, diamonds, and clubs. So I have one of those 4 aces. I only want one of them. So I'm looking for, out of 4 aces, I just want one. So 4 combination 1. Because it doesn't matter which one I get, as long as I get one of them. Now, out of the other cards, it does not matter what other cards I get in my deck, as long as I am not getting one of those 4 aces. So out of those 52 cards, 4 of them are aces. So that leaves 48 other cards for me to choose from. 48 other cards that I'm hopefully dealt. And I'm getting 4 out of those other cards. So it'd be 4 combination 1 times 48 combination 4 divided by 52 combination 5. So once again, this is our possibility of drawing an ace. This is our possibility of getting 4 other cards that are not aces. And this is our total possible hands that we could arrive with. So out of 4 combination 1, that's going to be 4 times, or that's going to be 4 possibilities because we're only choosing 1 out of 4. 48 combination 4, we'll have to put that one in the calculator though, because I don't know what that is. So combination 48 comma 4, that gives us 194,580 possible combinations, which seems pretty likely. 194,000, I apologize. 194,580. So we have a pretty big number in the numerator, which means we're going to hopefully get a larger number. Let's see how 52 combination 5 is. How many possible 5 card hands can we arrive with? Well, if we have 52 comma 5, there are a potential of 2,598,960 different hands we could arrive with. 2,598,960. So those are the total number of different 5-card hands we can get. This is our probability of getting, or this is our desired outcome of getting a single ace 4 times. So we can put that in the calculator. We have 4 times 194,580 divided by, I guess this is, if we put that in parentheses, then I hit divide, that's all going to be my numerator, divided by my number I just got, 5298960. So we have our 4 times our 194,580 divided by our 598,960, and we get 0.299. So we actually have, there's a 30% chance, pretty much, very close to a 30% chance that we are dealt an ace, just a single ace, which is actually pretty good odds. So if you think about, aces are pretty good in most games that you're playing with. So your odds of getting dealt an ace is pretty high, assuming you're getting dealt 5 cards. Let's look at this last example. So let's take a pause and consider the famous problem in probability theory. Suppose you have a room full of 30 people. What is the probability that there is at least one shared birthday? So you have a room of 30 people. What's the odds of having at least one shared birthday? What's the odds of having at least 2 of those people in the room share a birthday? And we don't care if there's 4 people in the room that share a birthday, 3 people, as long as there's at least one. We can then take this and see how it works for our class at the end. So what's the odds of 30 people sharing a birthday? Well, let's start. 30 is a big number, so let's start a little bit smaller and let's work our way up to 30 in order to help us grasp how to solve this. So we think about, let's say, what's the odds of having, in a room of 3 people, what's the odds of 3 people, at least 2 of them sharing a birthday? Potentially all 3 of them. Well, that can be kind of hard to calculate. An easier way of calculating this is thinking about what's the opposite, what's the alternative of that happening? What's the odds of having, in a room of 3 people, what are the odds that none of them share a birthday? Let's start with that. That's probably going to be easier. So it's probability that 3 people equals no shared birthdays. So in our room of 3, what's the odds of having no shared birthdays? Well, if we think about it, the first person in that room, they could have any possible birthday they want. They could have any possible birthday, which is essentially, out of 365 days, they can pick 365. That second person in the room, they can have any possible birthday they want, except for the birthday of that first person. So they could have 364 days out of 365 options. And that third person in the room, they can have any other birthday as long as it's not the first 2. So they have 363 days out of 365 options. So if we were to multiply this together, this would give us this would tell us how many birthday, or how likely it is for 3 random people to not share a birthday, that none of them have the same birthday. So we would have 365 over 365 times 364 over 365 times 363 over 365. So we can easily put that in the calculator. That would be 365 divided by 365 times 364 divided by 365. Oh, my thing is not being happy on me. Sorry, I need to go over. All right, times 364 divided by 365 times 363 divided by 365. And I'm hitting all the wrong buttons, 365. So the odds of that happening are 0.992 if we round up. So this, once again, this was the odds of not having anyone share a birthday. So if we were thinking about the probability of 3 people in a room, that they do equal, that 3 people at least have at least 1 shared day. If we think about it, it's a total probability of 1. If there's a 90 or 0.992 chance of not sharing a birthday, our probability of sharing a birthday would be 1 minus 0.992. If we remember, this is the complement event. It's the opposite of it happening. So in order to calculate the event, the complement of it, we just take 1 minus the complement, and that will give us our probability. So that is essentially 0.008, which is 0.8% chance. So less than 1% chance that 3 people in a room share a birthday. That's pretty, that makes sense, right? If you pick 3 random people, their odds of sharing a birthday sound pretty small. So let's try to scale this up a little bit. Let's use this to help us scale it up, to help us get closer to that 30. Let's scale it up to 5 people. All right, we're jumping up to 5. So the probability that 5 people share a birthday, at least share 1 birthday, that there is at least 1 shared birthday of 5. Once again, this would be the probability of 1. This would be equal to 1 minus the probability that 5 do not share 1 birthday. Which, once again, we can calculate that do not share. Because our probability of 5 do not share, we would calculate that just the same way we did up here, which would be 365 divided by 365 times 364 divided by 365 times 363 divided by 365. That's the exact same thing we had for the 3 days. Now we're just adding 2 other people. Now, once again, those 2 people, they just can't share birthdays with the other 5 people. So that gives us 362 over 365 and 361 over 365. Now, if we wanted to clean this up rather than having to type this, because if I think about it, I could technically calculate the probability of having 30 people not share a birthday by just plugging this whole thing and just keep going until I run out of, or until I get 30 numbers, which would just take a really long time. But if I want to clean this up a little bit, 365 times 364 times 363 times 362 times 361, this is really just the same as 365 permutation 5. Out of 365 options, and I choose a permutation of 5, that's what that equals. While 365 times 365 times 365 times 365 times 365, that is really just 365 to the 5th power. 365 times itself 5 times. So we can actually clean this up by calculating 365 permutation 5 divided by 365 to the 5th. This is very similar to that, very similar to our pin number problem that we had going on. So if we plug this into the calculator, we would have, first we would do our permutation. We would do 365 permutation 5 out of 365 days, choosing 5, divided by 365 raised to the 5th power. So this equals 0.973. Which, once again, that is our probability of not sharing a birthday. So our probability of sharing a birthday would be 1 minus 0.973, which we plug that into our calculator. 1 minus 0.973 equals 0.027. So there is roughly about a 3% chance that out of 5 people in a room, at least 2 of them share a birthday. But now that we have this figured out, we could use this strategy right here to help us calculate for 30. We can finally figure out our 30 number. So the probability of at least 30 people sharing a birthday would be equal to 1 minus the probability of 30 people not sharing a birthday, which we know is 1 minus probability of 30 people not sharing a birthday. It would be 365 permutation 30. Out of 365 days, we choose 30. As long, it doesn't matter which order they come in, as long as we have one different one for each of them. And then this would be divided by 365 to the 30th power. Because once again, it would be we'd have 365 in the denominator for each of those fractions, which would be 365 times 365 times 365 30 times. So if we plug this into our calculator, we can do 1 minus our permutation, which is we have 365 options. We are choosing 30 of them. Close our parentheses and divide that number by 365 raised to the 30th power. This actually gives us, because we already did the 1 minus there, 0.706, which is really close to around 70% of a chance. There's a 70% chance that out of a room of 30 people, at least 2 of them share a birthday. So if you could get 30 people and ask them all what their birthdays are, and you could like bet some money on this. Not that you shouldn't bet money on this, that's bad. But you could probably, there's a fairly good chance that you are going to have 2 people in that room, at least 2 people in that room share a birthday, which makes me wonder how many people in our class share a birthday. Let's calculate it. We'll talk about that after the video. So hopefully this video didn't run too long. I might have gone over a little bit. But let me know if you have any questions. We're going to practice this for the time.